Okay, so let's take a look at this check on strengths of acids and bases. So I've already gone ahead and answered number one, just in a T-chart. So strong versus weak, really the difference is in how they ionize. So strong acids and bases both ionize completely, or they dissociate into their individual ions. And so you can kind of see this in the diagram here. You see a strong arrow just to the right for both of these. And that's indicating that we are pushing all of those things from the acid or the base into individual ions. And so that's what happens with strong. With the weak acids and bases, what happens is they ionize partially, but not all the way, and so they form an equilibrium situation. So we represent that with that double arrow going in both directions. So the acid and base, the dissociation constants, so the Ka and the Kb, are also different for those. So we have very, very large ones for strong and very low values, generally speaking, for weak acids and bases. And so I have a couple examples there. When it comes to the strong acids and bases, you really do have to just memorize the strong acids. And so this is actually the list of them. These are all the strong acids that we consider. And then strong bases are just metal hydroxides. And so that's pretty easy to remember. So magnesium hydroxide, sodium hydroxide, potassium hydroxide. The interesting thing about metal hydroxides is that they aren't always very soluble, but what does dissolves completely into ions, and they're still considered to be strong bases. So we have a situation with weak acids or weak bases, and I'm just going to do this for the weak acids, so for a Ka value, where we can evaluate how much of them and calculate some values about what's happening at equilibrium under certain conditions. And so we're going to take a look at that. So in this first one, okay, it asks what is the Ka value for a 0.2 molar solution of an acid X or HX, which is just a generic acid with a pH of 2.0. So these are really interesting to solve because we're going to use something called an ice table. I'm going to draw one out here for us. So an ice table, ICE really just is an acronym that stands for initial, change, and equilibrium. Okay, so here's my table. So I have my columns and some rows here. Okay, so we're going to have our I here, our C here, and our E here. So initial, change, and equilibrium is what that stands for. And I'm going to go ahead and do a generic weak acid dissociation equation up above it. I always like to have my equations up there. So HX forms H plus X minus. And this is when we actually dissolve them or put this particular acid into water. Okay, I don't usually show the water. We can. There's a method for doing that, but I like to keep it as streamlined, as simple as possible. So we're going to create our table here. So our initial concentration for our acid is this 0.200 molar. So I'm going to do that right here, 0.200. And initially, when we put this into water, we don't have any concentration of either of the H plus or the anion. Okay. So we need to know what the change is, and the change is actually determined by the hydrogen ion concentration. Okay. So in order to determine our hydrogen ion concentration, we have to take a look at the pH. Okay. So we want to take the hydrogen ion concentration if it's not given to us, and in order to find that hydrogen ion concentration, we have to take 10 to the negative pH, just like we did in our previous calculations. And so that's going to be 10 to the negative 2.0. When I put that in there, I get a value of, actually, let me go ahead and do that. So 10 up caret negative 2, and that gives me a value of 0.01, And if we're keeping those sig figs, we can add it there. I'm not really too worried about that, but that is going to be the concentration of our hydrogen ions at equilibrium, because that's the amount that we have. And so what we know is that that value goes here. Okay, so that's where this came from. And if that's where that came from, then this had to be added to by 0.0100. And since there's a one-to-one relationship between the hydrogen ion and the anion, the X, this also has to be plus 0.01. I'm going to go ahead and knock off the other zeros because I'm running out of room there. And that means that that had to come from this other side, so we have to take away 0.01 over on this side. To find out what we have at equilibrium, then we're going to add the initial and the change together. So I kind of always like to show that I'm adding these together. And so 0.2 minus 0.01 gives us 0.190. We know that this is the value at equilibrium from that calculation that we already did. And then finally, 0 plus 0.01 is going to give us 0.01 for our anion as well, our X minus. Now we can go ahead and plug this into a Ka expression. So we're going to write out our expression. So Ka is going to be equal to the concentration of hydrogen ions times the concentration of the anion divided by the concentration of the acid. So I go ahead and I plug in our values that we know we have at equilibrium. So Ka is equal to 0.01. And since I have two of them, you can times them by each other, or you could just say that that number is squared on the top. And we tend to see a fairly consistent process with that at this point in our problem solving. And then on the bottom by that 0.190. So let's go ahead and do the math on that. So 0.01 squared divided by 0.190. And I get a very small number. We want to apply sig figs, so I started with 3 sig figs in my original molarity calculation. pH is a little bit weird for significant figures. And they only give us 2 on that one. We can go ahead and just round this to 2 sig figs. When you take AP, or if you take AP Chem later on, we'll talk more specifically about sig figs with these, but let's go ahead and just use that smallest value for now. And we're going to make that 5.3 times 10 to the -4th then in our rounding. Okay, so there is our answer for number 2. Let's go ahead and do one more of these. And so in number 3, you'll notice that they actually already gave us the concentration of hydrogen ions, so we don't have to do that step that we did in number 2 to go from pH into concentration of hydrogen ions. It's already done for us because we have hydrogen ion concentration. So that makes this one pretty nice to work out. So you just kind of have to figure out whether you do or do not have that information. So we're going to solve for the Ka again, and this time we're given a molarity of 1.00 molar for our original acid. And again, you were given the generic acid. If you're given a specific one, you can use this generic equation to do that as well. So let's go ahead and write out our ice table. Okay, so our I, C, E, HX, H plus, and X minus. Okay. And this is really just a problem-solving organizational tool. So we know that we start off with 1.00, because that was the value we were given. We're putting this into water, so these start off with 0. for concentration. And that's just the standard way we write that, unless we have a common ion, which we haven't seen anything yet with that. And so then our change is going to be the hydrogen ion concentration. So this goes into the change. We're going to take that away, so subtract it from the left side of the equation. So 7.2 times 10 to the negative third. I don't have a lot of room there, and we're going to add that to this side. So plus 7.2 times 10 to the negative third plus 7.2 times 10 to the negative third. Okay. So that means each one of these is 7.2 times 10 to the negative third. Okay. And then the other one, when we subtract that, I went ahead and calculated that already. We get 0.9928. Okay, so we added these up to get this bottom. All right, now let's go ahead and stick that into our Ka expression. So Ka, again, is going to be the concentration of H plus times the concentration of X minus over the concentration of the weak acid, HX. So we'll plug those numbers in. Again, we can square that top one because they are the same. So if we multiply them by one another, I just find it's easier for me to write them out this way. Oops, to the negative third, excuse me. We're going to square that whole thing. And then on the bottom, 0.9928. All right, so let's do this in our calculator. 7.2 second EE to the negative third. I'm going to hit enter, and then I'm going to square that. Hit enter again, then I'm going to divide by 0.9928. And I get an answer of 5.2 times 10 to the negative fifth. So that's our value for Ka. 5.2 times 10 to the negative fifth. And that is how you solve weak acid calculations. It's also how you would do weak base ones if you had something like that. You just use the same principle, just with a Kb value instead.